Yeah, well, thanks everyone for coming, and thanks to the organizers for putting this all together and for the invitation to speak here. This is based on joint work with Rachana, Madhukara, and Hugh Thomas. So let me start with promotion. Promotion is this really nice bijective operator that acts on the set of linear extensions of a poset, and it was originally introduced by Schützenberger. He was using it to study the Robinson-Shenstedt correspondence, but now it's found other applications in algebraic combinatorics, and people also have just studied it on its own. So later, Heyman and Malvenuto and Reutenauer reformulated promotion in terms of these local toggle operators, and that's going to be the way that I'm going to formulate it as well. And I'm going to define promotion on the set of labelings of a graph instead of linear extensions of a poset. But this is basically the same thing, so it's not really a big deal. Okay. So first of all, let me say what these toggles are. So a labeling of an in-vertex graph G will be just a bijection from the vertex set to Z mod in Z. And I really want to use Z mod in Z here instead of like bracket in, because I want this to be a sort of cyclic object, because I'm going to define a sort of cyclic analog of promotion. Okay, so let me define lambda G to be the set of labelings of G. And if I have one of these labels I in Z mod in Z, then I can define this toggle operator tau I. And this is just a map from labelings to labelings. All it does is it says, look at the numbers I and I plus 1. And if they're sitting on adjacent vertices, you do nothing. And if they're sitting on non-adjacent vertices, you swap them. So here are some examples of this. I have this graph with 5 vertices, and this is some labeling. And if I do tau 1, that says, look at the numbers 1 and 2. They're sitting on adjacent vertices, so I do nothing. So here I just didn't do anything. But if I do tau 2 to this labeling, that says, look at the numbers 2 and 3. They're sitting on non-adjacent vertices, so I swap them. And here I'm doing tau 5, which says, look at the numbers 5 and 6, but we're working with Z mod 5Z, so really 6 is the same as 1. So I look at the numbers 5 and 1, they're sitting on non-adjacent vertices, so I swap them. Okay. So promotion can be defined as this operator that acts on labelings by just doing tau 1 and then tau 2 and so on all the way to tau n minus 1. So you just compose these toggles in this sort of natural order. And well, the reason I wanted to use Z mod in Z is so that I have this extra toggle tau n, and that allows me to define what I call toric promotion. So this is basically sort of the same definition, except at the end I have this extra toggle tau n. And even though the definitions of promotion and toric promotion are very similar, the dynamical properties can be very different. So I'm going to be studying this from like a dynamical point of view, where we're going to iterate one of these maps and see what happens over time. Okay, so here's an example of doing toric promotion. I start with, let's say, this labeling of a path graph. So I first do tau 1, so that says look at 1 and 2. They're on non-adjacent vertices, so I swap them. Then I do tau 2, so I look at 2 and 3. They're on adjacent vertices, so I do nothing. Then I do tau 3, which says look at 3 and 4. They're on non-adjacent vertices, so I swap them. Then I do tau 4, which says look at 4 and 5. They're on adjacent vertices, so I do nothing. And then I do tau 5, which says look at 5 and 1. They're on non-adjacent vertices, so I swap them. And so this entire process is one application of toric promotion. So here's an orbit of toric promotion. If I start with this labeling of this path graph and I do toric promotion, I get this labeling. If I do toric promotion again, I get this labeling. If I do it again, I get this labeling. And if I do it again, I get back to where I started. So this is an orbit of size 4 for toric promotion. And so the main result that I proved in the original paper that I wrote about 1.5 years ago about toric promotion is that if G is a forest with at least 2 vertices, and sigma is some labeling of this forest, then I can tell you exactly the size of the orbit of toric promotion containing sigma. It's going to be n minus 1 times t over the GCD of t and n, where t is the number of vertices in the connected component of the forest containing the vertex where the 1 is sitting. So you look at the number 1, it's sitting on some vertex. That vertex is in some connected component of your forest, and t is the number of vertices in that connected component. So in particular, if G is a tree, then T will always be n. So then you just get n over the GCD of n and n. So that's just n over n, which is 1. And this just becomes n minus 1. So when G is a tree, all of the orbits of toric promotion have size exactly n minus 1. So like up here in this example, this path is a tree with 5 vertices. And here I have an orbit of size 4. But in fact, if I chose any labeling to start with here, not just this one, I still would have gotten an orbit of size 4. Okay, so I presented this result at the pre-seminar at MIT, and Tom Roby was there, and he said, well, what would happen if you did these toggle operators, but in some different order? And I said, oh, I don't know. And then I looked into it, and I formulated a conjecture. So I'll tell you the conjecture in a minute, but let me just fix some notation here. So I'm going to fix a bijection pi from bracket in to z mod in z. Think of this as basically a permutation. Then permutoric promotion is this operator t pro sub pi that you get by doing the same composition of toggles, but in some permuted order. So you do tau sub pi of 1, and then tau sub pi of 2, and so on, all the way to tau sub pi of n minus 1, and then tau sub pi of n. And we can try to study the dynamical properties of this operator here. So it turns out to be relevant to consider the number of cyclic descents of pi inverse. So this I'll call d. So this is the number of indices I in z mod in z, such that pi inverse of I is greater than pi inverse of I plus 1. And the conjecture I made is that if G is a path graph, then the order of this permutoric, excuse me, this permutoric promotion operator is just D times n minus D. So notice that I'm specializing the graph to just being the path graph. So earlier I was looking at forests and trees, but here I'm doing something much more specific. And that's because when you go from toric promotion to permutoric promotion, things get much more complicated. So when you permute the order of the toggles, it gets a lot more difficult to analyze. So we really have to specialize the graph in order to have some hope of saying something nice about the dynamics. Okay, so I guess the spoiler here is that we do resolve this conjecture, but I'm actually going to tell you a stronger theorem. But before I do that, let me discuss the cyclic sieving phenomenon. So this was introduced by Reiner, Stanton, and White in 2004. And they say, let's suppose X is some finite set, and F is some invertible map from X to itself of order omega. So this just means that omega is the least common multiple of the orbit sizes of F. And let's say capital F of Q is some polynomial in the variable Q. Then we'll say that this triple, X, F, F of Q, exhibits the cyclic sieving phenomenon if for every integer K, the number of elements of X fixed by F to the K, so this is F composed with itself K times, this should be this evaluation of capital F at this root of unity e to the 2 pi I k over omega. So I think if this is your first time seeing the cyclic sieving phenomenon, it might seem a little bit technical and complicated, but really what it's saying is pretty simple. It's saying that you have this potentially very complicated orbit structure of this map F, which is maybe this complicated information, but you can encode it with just this single polynomial capital F. And this ends up being really nice when the polynomial capital F is relatively simple. So like if you can write down this polynomial in just one line, then it's like you're encoding this potentially very complicated information about the orbit structure of F with this just one polynomial that you can write down in a single line. So that's when this ends up being really nice. Okay. So as before, I'm going to fix this bijection pi from bracket in to z mod in z. D is the number of cyclic descents of pi inverse, and G is the path graph. So the main theorem that Rachana and Hugh and I prove is that, first of all, the order of permutoric promotion on the path graph is D times n minus D. So this resolves that conjecture that I had from the earlier paper. But in fact, we can describe the entire orbit structure with this cyclic sieving phenomenon. So here, this is the set of labelings of the path, and this is permutoric promotion. And this sieving polynomial here is n times d minus 1 factorial times n minus d minus 1 factorial. And then this is the Q analog of the number n minus d, but evaluated at Q to the d instead of Q. And then this is a Q analog of some binomial coefficient. Okay, so this might seem maybe a little bit complicated, but it's still, not that bad. You can kind of write it down pretty easily. It's just some numbers here, and then this is like the Q analog of a number and a Q analog of a binomial coefficient. It might not be really illustrative as to what this is actually saying, like, how this really describes the dynamics if I just show you this polynomial. So I guess in the rest of the talk, I'm going to try to give some kind of a hint of the types of ideas that go into our proof. The proof we give is actually kind of long and involved, and so I don't really have time to go through all of it here, but I can try to give some kind of a flavor of what we do, and hopefully that'll be sufficient. Okay, so first, I have this slide called gliding globs, and actually the whole point of me having this slide here in the talk is just to explain why the words gliding globs are appearing in the title of the paper and the talk. I'm not really going to go into this in too much detail for the rest of the talk, so maybe this isn't so important, but I'll go through it kind of quickly. Basically, we define this variant of Schützenberger. So if you're familiar with Schützenberger from the theory of standard Young tableau, you sort of like slide some numbers along. And this is something similar, except you're allowed to slide multiple things at once. So here I have my labeling of a path graph, and I put some of the numbers into these globs of liquid. And then the globs are going to glide along the path according to some rules that I'm not going to tell you. But in this example, the 3 glides through the 4, 5, and the 6, so it goes over here. And then the 9 glides through the 2, and then actually the 7 just didn't glide anywhere, it just kind of stayed put. And then there's this sort of extra step where the numbers in the globs of liquid get cyclically permuted, so the 3 becomes a 7, the 7 becomes a 9, and the 9 becomes a 3. Again, I'm not really explaining what I'm actually doing here. This is just some thing that we define, but the whole point of doing this is that it allows us to prove that all of the orbits of permutoric promotion have size divisible by the least common multiple of d and n minus d. And the reason for doing this is that we can transfer the dynamics of permutoric promotion into the dynamics coming from applying this infinite sequence of operators. So imagine starting with some labeling and doing tau d and then tau d minus 1 and so on all the way to tau 1, and then you go up and do tau d plus 1, and then tau d, and so on down to tau 2, and then tau d plus 2, tau d plus 1, and so on down to tau 3, and so on. So the point is that if you take this permutoric promotion, which is defined as a composition of n toggle operators, and you just compose it with itself many times, you'll get this long chain of these toggle operators, and you can rewrite it by just swapping adjacent toggles that commute with each other. So if you have 2 toggle operators that actually commute with each other, you can just swap them. Just do a commutation relation. And by doing that over and over, you can rewrite this composition in terms of, well, basically as this sequence of operators here. But the issue is that in order to know that the actual orbits of permutoric promotion can be rephrased in terms of this sequence of toggle operators, we have to know something about the divisibility of these orbit sizes. So this is sort of why we need this variant of Schützenberger. But anyway, let me now just focus on this sequence of toggle operators where we do the tau d and tau d minus 1 and so on. And I'm going to try to understand this in terms of sliding stones and colliding coins. Okay, so there's a lot going on in this picture. It took a really long time to make this picture. So I'm going to try to like pick it apart piece by piece. So first of all, in this example, n is 6. So you can see here, this is my path graph with 6 vertices, and I've called the vertices v1 through v6 from left to right. And here I have a labeling of this path graph, which is 6, 2, 4, 1, 3, 5, going from left to right. Okay. Now remember, I have z mod 6z, which is my set of labels, and I'm going to represent that with this cycle here. So think of the cycle as representing our set of labels. That's z mod 6z. And one way that I represented the labeling is just by drawing the labels under the vertices of the path, but I could also represent the labeling by saying that for each vertex vi, if it's labeled by some number j, then I'll put a little replica of vi on the vertex j. So for example, I have v1 is labeled by 6, so I put a little replica of v1 on the vertex 6. And v3 is labeled by 4, so I put a little replica of v3 on 4. You might have to turn your head upside down to see it because I sort of drew it that way. But anyway, so this is like another way of representing the labeling with these replicas of the VIs here. And okay, so now in this example, D, the special number D that I was considering, in this example, D is 3. And so I'm going to put these colorful stones on the vertices 1 through D. In this case, it's 1, 2, and 3. So I have these stones of different colors. And basically, the stones are going to keep track of which toggle operator I'm supposed to be applying. So in the first step, I apply tau 3. because remember, I start with tau d, and d is 3, so I start with tau 3. And when I do tau 3, remember tau 3 involves the labels 3 and 4. So I'm going to slide this gold stone from the 3 to the 4. And then in the next step, when I do tau 2, I'm going to slide this green stone from the 2 to the 3. And then in the next step, when I do tau 1, I'm going to slide the pink stone from the 1 to the 2. So that's what I did here. And then in the next step, I apply tau 4. So I move the gold stone from the 4 to the 5, and then I keep going. So basically, I just keep sliding the stones each step. At each point in time, I slide it one step clockwise, and I just go in the order gold, green, pink, gold, green, pink, gold, green, pink, and so on. Okay, so this is how the stones are sliding around on the cycle graph. And remember, when I apply the toggle operator tau I, what that means is I look at the numbers I and I plus 1 in my labeling, and if they're on non-adjacent vertices, I swap them, and if they're on adjacent vertices, I do nothing. So in this case, when I did tau 3, the 3 and the 4 were on non-adjacent vertices, so I swap them. And so then over here, when I look at these replicas, that means I should swap the replicas that are on the vertices 3 and 4. So here it was like V5 was on 3 and V3 was on 4, but I have to swap them. So V3 is now on 3 and V5 is on 4. And so one way you can think of this is the gold stone has the V5 sitting on top of it, but when it slides over, it just kind of carries the V5 along with it as it slides, and it sort of moves through the V3 here. But on the other hand, in the next step, when I do tau 2, so the tau 2 says, look at the numbers 2 and 3. Well, they're on adjacent vertices, so I do nothing. And that means that the replicas here, the V2 and the V3, should not move anywhere. So what happens is the green stone slides from underneath the V2 to underneath the V3. So it kind of leaves the V2 behind and slides underneath the V3. And then similarly, in the next step, when I do tau 1, the 1 and the 2 get swapped. So the pink stone slides over, but it carries the V4 along with it as it slides. Okay, and you can keep going. And finally, okay, so I need to explain what these coins are. So whenever I have the replica of VI sitting on some stone, I'm going to draw a coin with the same color as that stone on the vertex VI. So here I have the replica of V5 sitting on the gold stone, so I put a gold coin on the vertex V5. Here I have the replica of V2 sitting on the green stone, so I put a green coin on V2. And here I have the replica of V4 sitting on the pink stone, so I put a pink coin on V4. And in this step, well, the gold stone carried the V5 along with it, so the coins actually didn't move. But in this second step here, when the green stone slides from underneath the V2 to underneath the V3, that means that the green coin is supposed to move from the V2 to the V3. So the green coin moves over one step, and when it does it, it collides with this pink coin here. So I draw this little green star here to represent that these coins have collided when the green coin moved over one step. And then similarly down here, the gold coin moved over one step and collided with this wall on the right-hand side. So I draw this little gold star to represent that collision. And then if I keep going, you can see the pink coin moves over and collides with the gold coin here. So I have this pink star. So basically, we're recording these collisions. And so far, the definition of a collision is fairly straightforward. You might think, okay, it's just two coins collide with each other, or a coin collides with one of the walls on the left-hand side or the right-hand side. But actually, this isn't the full definition of what a collision should be. It took us actually a really long time to figure out what the correct definition of a collision should be in order to sort of get the right definition for our purposes. So there are these other weird situations that we have to consider to be collisions as well. For example, if a coin sits against the wall for a really long time, then after a specific number of steps, it kind of just spontaneously collides with the wall again for some reason that I'm not discussing. But an example of this would be if I look at this gold coin here, it's kind of just sitting against the right-hand wall. And then if I keep just continuing this example, eventually it kind of just spontaneously collides with the wall again. And we have a rule for describing when this actually happens, which I'm not going to go into. But the point is, there's some way of defining these collisions. Okay, so now you might be wondering why I'm doing all this and why I'm defining these collisions in the first place. The reason is that we then define, okay, there are a lot of definitions in this talk. I'm sorry about that. It's kind of just a, necessary, I guess. But we define this Hasa diagram here of this poset. So the elements of the poset are all of the collisions that occur in this sort of bi-infinite timeline of stones diagrams and coins diagrams. So what I mean by this is if I start with this labeling, I can just do this process I was describing where I keep doing the toggles, and that'll generate this sort of infinite sequence of these stones diagrams and coins diagrams. I could also go backward in time by just reversing the order and just going backward. And so I get this sort of bi-infinite sequence of these stones diagrams and coins diagrams, which I'm calling a timeline. So this here is like a piece of a timeline. And if I look at all of the collisions that occur in this bi-infinite timeline, I can arrange them in this poset. And the way that we define the order relation in the poset is we say if there are two collisions such that there is a coin involved in both of them, then the one that occurred first in time is less in the poset. So as an example, these are two collisions that would both involve the green coin. I think this was where the green coin collided with the left-hand wall, and this was where the pink coin collided with the green coin. But this one occurred first in time, so I put it less than this one in the poset. So anyway, you get this bi-infinite poset that looks like this. And it will always have this kind of shape where it looks like a chain link fence. In this case, the width of the poset is 3. Like it's, 3 from like 3 edges going from the left-hand side to the right-hand side. And that's because D is 3 in this example. The special number D in this example is 3. But in general, the width will be whatever D is. And okay, so we get this bi-infinite chain link fence looking Hasa diagram. And I've labeled the edges. The way that I label the edge here is that it's just the distance between the locations where those collisions occurred. So here in this picture, these two stars are representing some collisions that occurred at some different times. But if I look at the locations where those collisions occurred, the distance between those locations is 3, which is why I labeled this edge with 3. And similarly, the distance between the locations where these two collisions occurred would be 1, and so on for the other edges. And so one of the key lemmas that we prove is that if you look at one of these half diamonds on the right-hand side or the left-hand side of this picture, so like a half diamond would be like this here or this here, the two edges in the half diamond will always have the same label. So here you can see it's like 1 and 1, or here it's 2 and 2, over here it's 3 and 3, or 2 and 2. And also, if I look at one of these little diamonds in the Hasa diagram, the opposite edge labels will be the same. So here I have 3 and 3 and 2 and 2 in this diamond here. If I look at this diamond, I have 1 and 1 and 3 and 3. Okay, so this is really one of the key lemmas that we prove. And okay, I have one more definition to give you, which is that of a transversal. So a transversal is just where we start at one of these left endpoint collisions here, and we just go up and to the right step by step until we get to the right-hand side. So this in blue, this little blue rectangle, that is a transversal, or this red rectangle here, that's another transversal. And when you read the edge labels on a transversal from left to right, you'll get a composition of the number n into d parts. So in this example, n is 6 and d is 3. And you can see that 2, 1, 3 is a composition of 6 into 3 parts. And similarly in red, 1, 3, 2 is a composition of 6 into 3 parts. And if you use this key lemma here that I mentioned, then you can show that when you go up one transversal, like if I go from the blue transversal up to the red transversal, then the associated composition just gets rotated one step to the left. So here I have 2, 1, 3, but if I go up, it gets rotated to 1, 3, 2. If I go up again, I would get 3, 2, 1. If I went up again, it would get rotated back to 2, 1, 3, and so on. So really what we've done here is we've said that if we start with just this labeling here, we can construct this bi-infinite timeline, and we can look at all the collisions that occur. From those collisions, we get this Hasa diagram with this edge labeling. And then we can get this orbit of compositions of n into d parts under rotation. So from this timeline, this bi-infinite timeline, I end up getting an orbit of compositions under rotation. Okay, so let me just fix a little bit of notation. Comp d of n will be the set of compositions of n into d parts. Rot will be this rotation map that just rotates the composition one step to the left. So one of the first results in the theory of cyclic sieving, which appeared in the first paper about cyclic sieving, is that this triple exhibits the cyclic sieving phenomenon, where you have compositions of n into d parts. This is rotation, and this is the Q analog of a binomial coefficient. And you might remember that this Q analog of the binomial coefficient was appearing in the main result that I presented earlier, that Hugh and Rachana and I proved for our cyclic sieving result. And that's basically because we get this map, which I just described, that goes from this bi-infinite timeline of stones and coins diagrams, and it produces an orbit of compositions under rotation. Okay, so we get this map here. The only thing is we have to check that each orbit of rotation actually has the correct number of pre-images under this map. And that is quite a bit more difficult. So that requires a lot more work. I'm not going to go into it in this talk because I'm pretty much out of time. So I'll just say that it involves a sort of delicate inductive argument, and we leverage the symmetries of the cycle graph in a special way. But yeah, it's too much to present here, I guess. Anyway, hopefully this gives some kind of a hint of the main ideas that we use. I'll just mention one open problem, which would be to try to look at permutoric promotion on graphs that are kind of similar to a path. So you could take this graph here, which it's like a path with an extra little edge there. You could call this the Dinkin diagram of type D, but I don't know if there's any reason to actually think of it like that in this context. Anyway, that is everything that I have to say. So thank you.
Thanks, Colin. If you have any questions, just feel free to ask or put it in the chat.
Colin, I had a question. So
Yes.
Nice talk. Thanks. So
Thanks.
rather than looking at other graphs that are similar to the path, what about going in the totally opposite direction rather than taking the path which has maximum diameter? Would this kind of promotion work nicely on a star?
Oh, yeah. So I think a star is also nice.
Okay.
Yeah. So I think you could understand the star, and that actually I think is not too difficult. The path was much more difficult than the star,
Gotcha.
but yeah.
Okay, good.